Welcome to the AtlantECO Podcast, where we talk about the science behind the AtlantECO project, the Atlantic Ocean, and the human adventures experienced along the way. Here, we have conversations with guests from around the world who work together so that we can better understand, manage, and protect the ocean. So let's embark on the journey of AtlantECO and discover the world that lies above and beneath the surface of the beautiful Atlantic Ocean. Welcome back to the AtlantECO Podcast, and in today's episode we're going to talk about a hot and important topic. Indeed, with our guest Thomas Frölicher, we are discussing mega heat waves in the Atlantic. This is a phenomenon that is observed more and more, and today we'll discuss why this is happening, the consequences it has, how it is monitored and modeled, as well as what we could expect in the future. But first, let's get to know our guest. So, Thomas, hi, and welcome to the podcast. I'm pretty excited to have this conversation with you today.
Hi, Eloise. Yeah, thank you very much for the invitation. I'm also very happy to chat about one of my favorite topics, marine heat waves.
Yeah, and before we get into the depth of that topic, I'd like to get to know you a little bit more. So could you tell us about where your connection with and your interest in the ocean started, and how it has evolved over the years to bring you to what you're doing today?
Sure. So I'm Thomas Frölicher. I was born in Switzerland, which is a landlocked country. So I do not really have a really particular good story to tell you why I became an oceanographer. But as a child, I actually often went to the basement, to the workshop of my father, who was an electrical engineer. And he was really into physics. And probably that's where I developed my own sense of scientific curiosity. And I also really love to go out to nature for hiking and swimming. So I actually then studied environmental science at ETH Zurich, which somehow combines these two topics, math, but also the nature. And I focused there on atmospheric physics. So there was no oceanography class at that time at ETH provided to the students. So I focused on atmospheric physics. And then I went to the University of Bern to do my PhD in oceanography, focusing on dissolved oxygen, which was a not well-known topic yet for many people at that time. So we were looking at why the ocean oxygen concentration is actually varying in the ocean, if it's due to human-caused global warming, or is it just due to natural variability. So I run one of the first fully coupled Earth system models in a large ensemble simulation mode. And we somehow showed that there are some large variation in oxygen occurring in the ocean, but the main trends, the long-term trends, are due to human-caused global warming. And then after my PhD, I went to Princeton University, where I worked with Jorge Sarmiento, mostly on the Southern Ocean. So we showed there that actually, the Southern Ocean takes up most of the excess heat which accumulates in the Earth system. Basically, 75% of all the heat goes into the Southern Ocean, and about 40% of the anthropogenic carbon the ocean takes up goes into the Southern Ocean. We also showed that the models we had at hand at that time were not really good. They had large uncertainties, and it was then the time where the SOCOM project was launched with the goal of deploying bioargo floats. So these are these robots which measure H+, but also temperature and salinity in the ocean to really get a better sense of how the Southern Ocean carbon and physical environment changes with global warming. And there I got really inspired about the ocean, and then I stick to that topic. I went back to Switzerland, first to ETH Zurich, and then I started my professorship in Bern again. I went back to Bern, where I focused on ocean extreme events. Yes, which is probably the topic we are talking about in the next few minutes.
Exactly. An unusual journey, I guess, because up to now, everybody had a story or connection with the ocean, but I guess yours just evolved over time.
Yes.
Yeah, so as we mentioned, today we want to talk about marine heat waves, and more specifically mega heat waves in the North Atlantic. So to begin with, could you explain what marine heat waves are and what we are currently observing?
Sure. So we know that heat waves occur over land. We are really well experienced with this phenomena over land. But over the last 10 to 15 years, we somehow also realized that heat waves can also occur in the ocean. And they can have dramatic effects on different things, on ecosystems, but also on weather patterns, and then also on weather patterns actually over land. So a marine heat wave, in general terms, is just a period of persistent, anomalously warm ocean temperatures. Technically, we define that when sea surface temperature, so we often look at sea surface temperature, but you could also define a heat wave below the surface. So when the temperature exceeds a seasonally varying threshold for at least 5 consecutive days. So if the temperature is really hot relative to normal conditions at that time of the year, and then we call that a marine heat wave. And if we have defined then that event, we can look at different properties like the duration of such an event, the intensity of the sea surface temperature anomalies, or also of the frequency of these events, how many times they occur during the year. These marine heat waves have occurred over the last few decades in all ocean basins, and they are caused by a range of drivers. So generally, they are caused by enhanced air sea heat uptake. So you have more heat which goes into the ocean than it's left from the surface ocean back to the atmosphere. But they can also be caused by changing ocean currents, by less mixing, for example, or just by a displacement of ocean currents towards north or south, which then leads to anomalous warm water in some regions and in cold waters in other regions. And coming now to the situation today in the global ocean, so it's quite concerning what we see. So the global sea surface temperature currently is really at record high conditions relative to temperatures since the start of the instrumental record, since 1982, where we have the satellite record. So at the moment, the global ocean is 21.1 degrees warm. This is 0.4 degrees warmer than ever measured since the last 40 years. And that's quite a big anomaly, I would say. And when we look at marine heat waves, about 30% of the global ocean experience now a marine heat wave. And that's also quite a lot. And especially when we look then at the regional scale, it's especially the North Atlantic, which has a really warm temperatures at the moment. It's about 0.5 degrees higher than ever measured before. The Mediterranean Sea also had record high temperatures in July. And I realized that by myself when I was at the summer school in Trieste, end of July. I also went swimming. It was really hot. It was not really cooling me down anymore. And there were also other parts of the ocean which were really extremely hot. For example, in the Florida Keys, the temperatures were almost 38 degrees, actually. So it was really hot. And this is really quite unusual. And another thing which is quite unusual is that if we look at the global sea surface temperatures over the year, usually the peak of the temperature is in March because most of the water is actually located in the southern hemisphere. And in fall time, then you have the highest temperatures. But this year, really, we have the peak actually in August. That's because the northern hemisphere oceans are so hot that actually the peak in the seasonality has reached for the first time actually in August and not in March. So it's really unusual this year compared to other years.
So quite concerning, right? And yeah, you mentioned the technologies involved. So we have records from satellites and maybe Argo floats and these kinds of things. So can you explain a little bit more how these heat waves are research monitored and how you model them as well?
Sure. So for looking at heat waves, we need data sets which have high temporal resolution and which are long enough to actually say something about rare events, because extreme events only occur at some certain times, but not so often. So we need a long time series to really identify extreme events. Mm. So that's actually also one of the reasons why this topic has emerged just in the last decade, because the satellite record has been established in 1982, these satellite measurements, and now we have more than 30 years And 30 years, we usually say, well, we have a long enough record to say something about rare events. And for looking at marine heat waves, we also really need daily data or sub-daily data and not just monthly data. So we need these satellite data, but they are all usually combined with Argo floats or with buoy data and other time series which are available. And then we use usually ocean models or fully coupled models to say something why things have changed. So in my case, I often use fully coupled models, which are kind of these complex Earth system models, which have an ocean, atmosphere, land, and sea ice component. Sometimes also a land ice component, where we run these simulations with observed CO2 concentration or emissions, and then we can say something about how things have changed in the historical period. We know that the ocean takes up most of the excess energy, about 90% of the excess energy, which accumulates in the Earth system due to the increase of greenhouse gases, actually goes into the ocean. And that has led to an increase in sea surface temperature of about 0.9 degrees since the pre-industrial times. And for a lot of people, 0.9 degrees is not so much. And also kind of these record high temperatures of about 0.4 degrees higher than usual sounds also not like much. But we need to remember that actually we need a lot of energy to warm up a liter of water compared to a liter of air. So we need 3,000 times more energy to warm up a liter of water by 1 degree than a liter of air by 1 degree. So you need a lot of energy because of the higher heat capacity of water to actually warm up the ocean by just a small amount. And because the ocean takes up so much of the excess energy, that's one of the reasons why we see now these record temperatures. But these are not the only reasons. There are other reasons which have now actually led to these high record temperatures. The most important process globally is the El Niño Southern Oscillation. And the WMO has just recently announced that El Niño conditions have developed for the first time in 7 years. So the tropical Pacific sea surface temperatures are anomalously warm. And because of the heat which has been redistributed from the west to the east across the Pacific, which has led to that warming. But that can actually not explain why the North Atlantic is so warm at the moment. And there are somehow floating different hypotheses around in the scientific realm why that is. And one of the most, I think I would say, most convincing hypotheses is that we had less strong westerlies over the last few months over the North Atlantic. So if you have less winds, that leads to less mixing of cold waters to the surface. And so there was less potential to actually mix the warm water down to the deeper ocean and to bring up colder waters back to the surface ocean. So that was one of the reasons why the North Atlantic was actually able to warm up that quickly and that strongly over the last few months. There are other reasons where researchers have said that could be a potential contribution. For example, like less Saharan dust. So if you have less dust coming from the Saharan desert to the open ocean of the North Atlantic or the tropical Atlantic, that would actually lead to more incoming radiation hitting the ocean surface. And that could also warm up the ocean surface. That could also be a reason. And then there are other reasons like volcanic eruption last year, the Tonga eruption, or shipping regulations, which had led to less sulfate aerosols, especially in the North Atlantic, which would have led then to more warming of the ocean surface. But I think these are all hypotheses, and we do not know yet the quantification or the relative contribution of these different factors leading to the high temperatures in the North Atlantic. But I think in the next few years, we will know more about which contribution is the most important contribution. Yes.
And just listening to that, is there anyone looking at all of these different things, comparing all of these things together? Because I guess each team researches their own, but is anybody looking at all of them at the same time?
Yeah, so for example, we have a research focus group from the CLIVAR, a marine heatwave research focus group. So that's one of our goals, to look at these together. So we have actually scientists with different expertise to look at that problem. And it reminds me a little bit at the hiatus problem, like from 1998 to 2012, where the global temperature has not really increased that much over that period. And then all the different disciplines somehow put forward their hypothesis why that was actually the case. And then now it's somehow a similar thing in the Atlantic Ocean. Why is it actually so warm? So all the different research fields have their own hypothesis. But as you said, it's really important that we are coming together and try to solve that together.
So now let's turn to the consequences and to understand what impact we might already be observing. And on what in the ocean. It could be on marine life or on the physical condition of the ocean, and also what can we expect in the future.
So actually, when we look at the forecast, so there are seasonal forecasts available, how the sea surface temperature will develop over the next few months. So there is actually a 50 to 80% chance that the marine heat wave in the tropical Atlantic will persist throughout the winter. And the longer a heat wave actually exists, we can expect the bigger the impacts will be. So what are potential impacts? We know from previous events that ecosystems are really sensitive to high temperatures, and marine heat wave can result in billions of US dollars in damages to marine ecosystems and to industries such as fisheries or tourism and so on. And especially marine heat wave, we have seen in the past, can cause heat stress on a variety of marine species, including foundation species like seagrass, but also kelp forests and corals. And one of the best known and best studied marine heat wave was the blob in the Northeast Pacific from 2013 to 2015. That was a massive marine heat wave, the longest ever recorded. And this massive heat wave led to mortality and reproductive failure of seabirds, for example, mass stranding of sea lions in California, but also of whales in Western Gulf of Alaska, and also then to shifts in species distribution towards warm water species, which then had implications for fisheries. Some marine populations have not recovered since then, so they can also have long-lasting impacts. However, we also need to be a bit careful that not all of the heat waves will actually have an impact on, for example, fish. So we just had a paper published where we actually showed that marine heat waves are not the dominant drivers for demersal fish biomass, for example, at the east coast of the US in the Atlantic Ocean. So there actually the variability in the fish biomass is too strong to see any signal from marine heat waves. And we also have seen, for example, that the Northeast Pacific, where we have seen these big impacts, it was not just the heat wave which have occurred, but also the other ocean conditions were extreme at the same time. So ocean acidity, so the pH was extremely low at the same time, and the oxygen concentration was also extremely low at that time. So maybe some of the impacts we have seen were not only caused by the thermal stress, but also by other stressors. And that's also something we are actually looking at in AtlantECO, at so-called compound extreme events, when actually different conditions are extreme at the same time and at the same location. And we have shown, for example, in the Atlantic, that especially in the subtropics of the Atlantic, often when a heat wave occurs, also high acidity extreme events occur. So we can expect that even though we do not have the observations at hand at the moment, that the current heat wave which occurs in the subtropical Atlantic co-occurs with high acidity conditions at the moment, and possibly also with low oxygen conditions. And these compound events, I think that is something which we are really worried about, because when you have...
That's a good transition into my last question for you today, actually. So looking more of AtlantECO project, to understand how this kind of data and information that you're gathering and the models you're using, how is it integrated into our research and how it will help us get the resources we need to achieve a better management of the ocean and of its resources?
Yes, so in AtlantECO, I'm actually involved in a work package which assesses these extreme events in the Atlantic Ocean, but not only extreme events in temperature, but biogeochemical extreme events in general, and how they impact on ecosystems. And we have shown, for example, that in some regions, the likelihood that these extreme events co-occur are higher than in other regions. And they actually are associated often with large-scale climate modes, such as the NAO. So in a positive phase, you have a higher likelihood, and in a negative phase, you have a lower likelihood in some regions, and in other regions, the opposite. So with this information, actually, hopefully will help the communities to plan how to best reduce the risk. If, for example, the NIO goes in a certain state, because we know if the NIO goes into a certain state, then the likelihood of these extreme events will increase. And in other regions, it actually will decrease. And the same is actually true for other regions. So we know now the drivers of these extreme events. Based on this data we have analyzed and also the models we have at hand. And with this driver information, we can then actually help the communities to reduce the risks of harmful impacts of these events.
So a lot of information to take in. So thank you so much for taking the time and explaining all of this fascinating world. And of course, we're carrying the work in AtlantECO. We've still got a couple of years to run. And then maybe we can come back to you towards the end of the project and see what has emerged and what the data is looking like.
That would be a really big pleasure.
So thank you, Thomas, for today. And let's keep the work going.
Thank you.
We hope that you've enjoyed today's episode and look forward to seeing you next time. You can follow the AtlantECO project on our website on www.atlanteco.eu, and you can also find us on Twitter, Instagram and Facebook. All the links and information on the project and on today's episode is in the show notes. AtlantECO is a project funded under Horizon 2020, a European Union research and innovation programme.